Today, I'm bringing you truly special content, an exceptional interview, a debate between two true giants of modern science on one of the most fascinating and challenging topics ever, the enigma of quantum mechanics. From the measurement problem and the double-slit experiment, passing through the multiverse theory and the phenomenon of entanglement, up to the vision of superdeterminism. Discussing all this are two brilliant minds. On one side, we have Sabine Hossenfelder, theoretical physicist, researcher, best-selling author, and creator of a famous YouTube channel. On the other is Matt O'Dowd, an astrophysicist specializing in black holes and galaxies, professor at City University of New York, and also a YouTuber. In short, an unmissable debate that I have translated and that we will comment on just for you. Before we begin, if you love science and big questions, I ask you to subscribe to my channel and activate the bell. Thank you. And now, are you ready? Let's go. The interview begins in a very personal way. Matt asks Sabine what her first experience with quantum mechanics was. As Sabine says, her training was very traditional, summarized in the motto, "Shut up and calculate." She was taught to use the mathematics of the theory without asking too many questions about its profound meaning, about the interpretations. It was only later, working on quantum gravity and seeing that progress was slow, that she began to think that the problem was not in gravity, but in our way of understanding the foundations of quantum mechanics. As Matt says, however, for him, quantum mechanics was a revelation. After Newton's classical physics, so predictable and mechanical, almost a clockwork universe, the double-slit experiment was like a crack of light in a mechanistic world. He thought, wow, magic is real. Although he then admits that quantum mechanics is not magic, it was that sense of mystery that captivated him before he dedicated himself to astrophysics because quantum mechanics was too difficult. And the heart of this mystery, on which both agree, is the so-called measurement problem. This is perhaps the main problem of modern physics. And Matt explains it very well with the double-slit experiment. A single electron, launched towards two slits, behaves like a wave that passes through both simultaneously, creating an interference pattern in bands on the screen behind. But the moment a measurement is made, this probability wave collapses and the electron appears at only one point, like a particle. The question is, what happens at that moment? What is a measurement? And why does our act of observing change the behavior of reality at such a fundamental level? It's an idea that sends shivers down your spine because it seems to give us, observers, an active role in defining reality. But let's go back to the interview. Sabine highlights two aspects of the strangeness. The first, already noted by Einstein, is that this collapse of the wave must occur instantaneously everywhere, faster than light, which he called spooky action at a distance. The second, even stranger for her, is how does the particle know in advance if we will decide to look from which slit it will pass? It almost seems like it can predict the future. And here we enter the field of interpretations. As Matt says, the standard one, Copenhagen, simply states that things work this way, focusing on mathematical calculation for practical purposes, avoiding explaining why or how. Others, like Bohm's theory, introduce the concept of a pilot wave as a physical reality that guides particles. But the problem of non-locality remains. And then, there's the famous mini-worlds interpretation, according to which every possible outcome of a measurement occurs, but in a separate universe. But the crucial point, on which the 2022 Nobel Prize in Physics was based, is entanglement and Bell's tests. As Matt explains, two entangled particles remain mysteriously connected. If you measure a property of one, you instantly influence the same property of the other, even if they are light years apart. Bell's tests have shown that this correlation is stronger than any local and realistic theory could ever explain. And this is where Sabine Hossenfelder introduces her idea, superdeterminism. As Sabine says, Einstein's error was not in looking for an underlying reality, hidden variables, but in not considering another possibility. Superdeterminism states that particles have defined properties from the beginning, and therefore there is no spooky action at a distance. The theory is local. But then how do you explain the correlations in Bell's tests? The answer is that not only the state of the particles is determined, but also the choice the experimenter will make. The choice of which measurement to perform is not free and independent, but according to Sabine, it is correlated with the state of the particles from the beginning of time. And this is that moment when the brain starts to smoke. Superdeterminism saves locality, but it does so at too high a price. The denial of free will. As Matt objects, it's difficult to imagine a mechanism by which a scientist's decision could be so precisely correlated with a particle emitted who knows where and when. Sabine replies that this correlation is not something to be explained, but the basic assumption, the axiom from which the theory starts. It's a radical idea, which overturns our deepest intuitions, but she considers it the most logical solution. The debate then shifts to the most important question: how can we decide who is right? As Sabine says, there is only one answer: with experiments. Theories like superdeterminism, unlike other interpretations, make slightly different predictions from standard quantum mechanics in extreme conditions. For example, they could predict exactly when and how the wave function collapse occurs. The problem is that at the moment, technology, like quantum computers, is not yet advanced enough to test these predictions. This is a crucial point that shows us how science works. For a century, we have discussed philosophy and interpretations, but we are reaching a point where technology could allow us to transform these philosophical questions into experimental questions. We might be able to ask nature directly what the correct interpretation is. It's fascinating to think that we might see the solution to this enigma in our lifetime, as Sabine hopes. This demonstrates that physics is not a set of dogmas, but a continuous process of questioning, debate, and, finally, experimental verification. In conclusion, Sabine connects everything back to her starting point, quantum gravity. She thinks that solving the measurement problem is the key to unifying quantum mechanics and general relativity, because a collapse mechanism could prevent the theory from breaking down at very high energies where it currently fails. So, what does this debate leave us with? It leaves us with the awareness that the foundations of our reality are still an unexplored territory full of mystery. There are radical ideas like superdeterminism that challenge our notions of cause, effect, and free will, but which could solve some of the greatest paradoxes in physics. It shows us that science is alive, a heated debate between brilliant minds who, despite opposing ideas, seek the same thing: a deeper understanding of the universe. Perhaps we will never fully solve the enigma, or perhaps the answer is just around the corner, hidden in an experiment that we do not yet have the technology to carry out. If you liked the video, leave a like and a comment with your thoughts, and don't forget to subscribe to the channel so you don't miss the next content. Bye.